Hello everyone, I'm Saraswathy Ramanathan. I'm going to present my work titled Latency-redundancy trade-off in distributed read-write systems. This is a joint work with Gaurav Gautam, Dr. Vikram Srinivasan, and Dr. Parimal Parag. Data is replicated and stored redundantly over multiple servers in distributed read-write system. This is done to prevent single-point failure and for the cost efficiency that such systems provide. Choosing the right system parameters can impact the performance of the system. For example, Amazon and Google loses 1.2% of its users to an additional delay of mere 0.5 seconds. We focus on the design of distributed read-write systems and optimize it for latency. We consider the distributed storage system with primary-secondary architecture. This is a common architecture used in commercial databases like MySQL, MongoDB, etc. In such a system, a request to write to a file is dispatched to the server denoted as a primary server. The primary server forwards the write request to the secondary server once it has completed the write. A request to read the file can now be sent to any of the servers in the system because each server has a copy of the data. Therefore, the read requests are sent to one of the servers in the system uniformly at random, resulting in distribution of the load. Since we wish to quantify the trade-off between latency and redundancy, we will check the impact of redundancy on both read latency and write latency. Read latency decreases with increase in redundancy. This is because read can now access data parallelly from any of the servers in the system. Write latency, on the other hand, increases with increase in redundancy because write needs to be completed at more number of redundant copies of the data. This leads to a natural trade-off between write and read latency with increased redundancy. Using system latency as a performance metric, we'll obtain the optimal redundancy for the system. We'll characterize the trade-off between latency and redundancy and obtain the optimal redundancy for the system. All prior works on distributed storage systems until now only consider read or write latency while assuming the other to be negligible. To the best of our knowledge, we're the first work to quantify system latency for distributed storage system, assuming non-negligible read and write. We'll illustrate the system model and introduce the notations here. We'll assume a system with Poisson arrival for read and write requests. We'll take the arrival rate of read and write requests as lambda r and lambda w respectively. Since the read load is distributed uniformly at random to the n+1 servers in the system, each server only receives lambda r plus n by 1. We'll denote the number of read and write requests at server I at time t as Ri of t and Wi of t respectively. As already mentioned, the write request joins the primary server queue first, and the primary server directs these write requests to the secondary servers after it has completed the request. And once the write request has been served by all the n secondary servers, the request will leave the system. This implies that the write process is an n fork join queue. We consider the read priority system where read request preempts the write request on arrival. A write request will resume its service when there are no more read requests at the queue in the server. We'll assume that the read and write requests are served exponentially at rate mu r and mu w respectively. We'll define Mn of t to be the number of requests at time t in the n+1 server system. This is nothing but the sum of the number of read and write requests at each of the server in the system. We obtain the limiting mean number of requests as Mn bar. Little's law states that the mean number of requests is equal to the product of the total arrival rate of the request and the mean latency of the request. Since the limiting mean number of requests is directly proportional to the system latency, minimizing the Mn bar gives the optimal redundancy n star of the system. This is because of the Little's law that was already stated. Denoting read and write load as rho r and rho w respectively, we only consider a stable system with load less than 1. It is already proved in Badita's work that an n fork join queue can be modeled equivalently as an n tandem queue system. So the system latency is equal to the sum of the latency from each of the tandem queue. We'll write the fork join system for our case. We can see that the server 2 and server 4 are free to serve the write request as the read preempts the write request in our system. On the other hand, server 1 and server 3 are not free to serve the write request and are busy serving the read request. The read process can be easily modeled. However, the write process is a fork-join queue which depends on the state of the read queue and the set of observed servers for each tandem queue. This is a complicated fork-join queue. We'll try to model the same as a tandem queue. If there were no read requests, the tandem queue for the previous figure fork-join queue would have looked something like this. However, in the presence of read request, server 1 and server 3 are not available to serve the write request. It is important to keep track of the set of servers that have served the write request in the tandem queue, because when server 1 and server 3 return back, they should serve the tandem queue with write requests that it is not already served. So we'll extend the state space to include the same. We define Sk of t to be the set of secondary servers that has already served write request k at time t. Sequence of set of observed servers for all forked write requests is S of t. State of the system at time t is given by Z of t equal to W0 of t, S of t, R of t. R of t is nothing but the number of read requests at each server in the system. It must be noted that Z of t is infinite dimensional. We prove that the random process Z of t for t varying from 0 to infinity forms a continuous time Markov chain. We give the associated generator matrix for the Markov chain. We have a system with infinite dimensional state space. We try to model this as a set of tandem queues. The number of requests in tandem queue I is equal to the total number of write requests with set of observed servers equal to I. Y of t is a pooled tandem queue whose service depends on the state of read queues in the system and the set of observed servers for each tandem queue. However, this process stationary distribution cannot be found easily. In fact, the stationary distribution can only be found by getting the eigenvector for an n-dimensional operator with eigenvalue unity, which is an NP-hard problem. Therefore, we'll approximate the Markov chain by a series of uncoupled tandem queues with service rate equal to the average service rate at each tandem queue. We give the expression here. From the expression obtained earlier, we obtain the closed form approximation for the number of read and write requests in the system. Differentiating the total number of requests in the system, we obtain the optimal redundancy n star. We numerically simulate the read priority system and obtain the optimal number of servers for the same. We compare the optimal number of servers that was obtained from the simulation with the closed form approximation that was given earlier. We fix either the read or write arrival rate while varying the other with a 95% of the stability region. We find that the simulation closely follows the approximation in both the cases. Going further, we perform an experiment on a locally created distributed read-write system. We plot the mean number of requests for such a system with read arrival rate 20 and write arrival rate 0.7. We observe a dip in the curve. This implies that there exists an optimal redundancy even in experimental setup. However, the experiment and simulation curve do not match due to the presence of non-idealities in experiment. For example, the non-homogeneity of the servers used and also the network delay. Next, we plot the mean number of requests for different service distributions. We fit different service distributions to the service distribution that was obtained empirically from the experiment. Once again, we notice the existence of an optimal redundancy even for non-memoryless service distributions. With that, we come to the end of the talk. We'll summarize our main contributions here. Thank you for listening.